Okay, what we do is we use equation 3737, which is the transverse Doppler shift formula, and solve for 1 over lambda, which is for the frequency, in this sort of a form right here. Then you rearrange this and solve for lambda minus lambda 0. And that is this right here, lambda, and it's 1 over the square root of 1 minus beta squared minus 1, right? And so this is 589 nanometers. 1 divided by 1 minus this value right here. And this is, there should have been a square root sign right here for this right here. This portion right here is under the square root sign, and this right here is not, okay? So there was a sign missing right here for this portion. Okay, and so it works out to be 2.97. Okay, so it's lambda 1 divided by the square root of this right here. So this is the first term, and then minus 1. So this is the first term, and this is minus 1. Okay? And somehow that didn't shape out right here. I did not get the square root sign right there over this portion right here. Okay. Now, next one. A spaceship is moving away from Earth at speed 0.2 times the speed of light. A source on the rear of the ship emits a light at wavelength 450 nanometers, according to someone on the ship. In other words, someone who's not colorblind. What is the wavelength and color, blue, green, or yellow, or red, as detected by someone on Earth watching the ship? Okay, so we have this equation right here for the frequency, which and then we used what we learned before in terms of the lambda there, right? And this is the equation that would result. Lambda equals the lambda 0, f0 over f, lambda 0, and the square root of 1 plus beta divided by 1 minus beta. So with this, with 450 nanometers and beta equals 0.2, it works out to be 1 plus 0.2 divided by 1 minus 0.2, right? And it's the square root of this value right here, which turns out to be 550 nanometers. And this is in the green-yellow portion of the spectrum, of the visible spectrum. Okay? Momentum and energy. In the relativistic mechanics, the definition of linear momentum is P, where this is the momentum, is not just our mass times velocity, but it now has to have this gamma factor, the Lorentz factor here as well. So this equation gives a direct, correct definition of momentum for all physically possible speeds. For speeds much less than the speed of light, it reduces the classical definition of momentum, P equals mv, right? So the object mass and the equivalent energy are related by E0 equals mc squared, which without the subscript E0 is the best known science equation of all time. I don't know. I think F equals ma should be up there pretty strong with that as well. Only this energy E0 is associated with the mass of the mass energy or rest energy. The second name suggests that E0 is as an energy that the object has even when it's at rest, simply because it has mass. And if we assume the object's potential energy is 0, then its total energy is the sum of its mass energy and its kinetic energy. Okay? So E equals mc squared plus k. And E equals gamma mc squared would be another way of looking at this. An expression for the kinetic energy that is correct for all physically possible speeds, including speeds close to the speed of light, is given by this equation right here. So it's mc gamma squared minus 1, the kinetic energy. And 1 over the speed term squared is the Lorentz factor for the object's motion. Connection between the relativistic momentum and the kinetic energy is thus given by PC squared equals K squared plus KMC squared, and E squared equals PC squared plus MC squared, and this term is squared. Okay? So the relativistic and classic equation for the kinetic energy of an electron plotted as a function of Vc right here. So this would be the classical right here, and this is what happens under the relativistic up this way, right? Note that the two curves blend together at low speeds, right? You have to get up to 0.6 times the speed of light for there to be a divergence here. Okay? So what's the minimum energy required to break a nucleus of a carbon-12 atom into 3 nuclei of 4 helium molecules each, atoms each? So we have Q equals the delta MC squared, right? And that right there is the change, 3 of these minus 1 of these, right? So you've got 3 helium, 1 carbon-12. That gives you this value right here. So this is the energy that must be supplied to the system to cause that carbon-12 nucleus to break up into 3 separate helium ions. Okay? Quasars are thought to be the nuclei of active galaxies in the early stages of their formation. A typical quasar radiates energy at the rate of 10 to the 41st watts. At what rate is the mass of this quasar being reduced to supply this energy? Express your answer in solar mass units per year. One solar mass unit is 2.0 times 10 to the 30th kilograms, which is the mass of our sun. Okay? So since the rest energy and the mass of the quasar are related by this equation right here, the momentum of the energy radiation and the rate of mass loss are related by the momentum equals d, the change in energy with change in time, which is the change in mass per unit time, times c squared. dm dt is p over c squared, right? P divided, both sides divided by c. Okay, and therefore it's 1 times 10 to the 41st watts divided by 2.998 times 10 to the 8th meters per second. Oh, this should have been a squared right here. I messed up on there. Time equals 1.11 times 10 to the 24th kilograms per second. Since a solar mass is 2.0 times 10 to the 30th kilograms, and a year is 3.156 times 10 to the 7th seconds, the change in the mass per unit time is this value right here, right, times this ratio right here, the number of seconds per year, divided by the kilograms of the sun. So it works out to be roughly 18 values of the sun released every single year. That's the quasar. So anyway, we have the postulates. This is a summary of the information and the equations, the time dilation, the Lorentz contraction, the Lorentz transformations when you've got the two bodies moving relative to each other, relative velocities of the different ones, the relativistic Doppler effect for light, the transverse Doppler effect, for if the light source is perpendicular to the line source, the momentum and energy changes, and so there's quite a few equations in this chapter. Most of them rely upon this 1 minus beta squared, 1 plus beta, 1 minus beta, the square root of that, or some variation on that. So that's what you have for this chapter. The following questions are to be answered along with the homework problems for Thursday. And Thursday, what I'll also do is I will give a quick review of different things for your test, your final test, which is next Tuesday, a week from today, is when you'll have your final exam. It will concentrate on the last 3 chapters. It'll be about half that, and then lesser amounts for the earlier materials covered. So anyway, I hope that was all helpful to you, and you did learn a little about relativistic physics today.